Let's begin our class now. We talked about network pruning last week. Today, we will talk about more methods that can reduce the size of the network. This method is called knowledge distillation. You will soon discover that the main idea of this technique is similar to network pruning. So knowledge distillation works like this. Train a big network first, which is called teacher network. In this method, it is the teacher. Then, train the small network, which is called student network. So you should train the big teacher network first, then build the student network according to the teacher network. In network pruning, the small network is created by removing or pruning some redundant parameters of the larger network. But knowledge distillation is different. This time, the student network learns from the teacher network. The two networks are named teacher and student is because of the learning relationship between them. But how does the student network learn from the teacher? Here's the answer. Suppose the task we are doing is handwritten number recognition. Throw all the data into the teacher network. Because this is a classification problem. So the output of the teacher should be a distribution. As an example, the output of this picture might be 0.7 for 1, 0.2 for 7, and 0.1 for 9, etc. Then, the student is given the exact same picture. But the student does not learn from the correct answer. It treats the teacher's output as the correct answer. That is, 0.7 for 1, 0.2 for 7, and 0.1 for 9. The student should try to output something as close as possible to the teacher's output. So it should try its best to output 0.7 for 1, 0.2 for 7, and 0.1 for 9. What if the teacher makes a mistake? Wouldn't the student learn something wrong? Yes, but the student doesn't care. Students learn from the teacher's answers. The student just learns wrong knowledge. If the teacher gave it a wrong answer, you might want to ask, why don't we train the small network directly? We added a step that can cause the student to learn something wrong. Why don't we allow the student network to learn from the correct answer? The reason here is the same as that of network pruning. Do you remember? Last week, I talked about why don't we train a small network directly. The most intuitive reason is that training a small network directly is not good compared to pruning from a large network. The same answer holds for knowledge distillation. Why not directly train the small network? Because directly training a small network is worse than letting the small network learn from the large network. In fact, this technique is relatively old. The most well-known article of knowledge distillation is published in 2015 by Hinton. Hinton is regarded as the proposer of knowledge distillation by many people because Hinton published the article, Knowledge Distillation of Neural Network. But I had read some papers that proposed the similar idea, even before Hinton. For example, this article, with a fancy title, Do Deep Nets Really Need to Be Deep?, is published in 2013. The authors also proposed the idea of network distillation. Obviously, this paper is published earlier than Hinton's. At that time, people doubt the power of deep learning. Therefore, you have to do research and write articles to justify the power of deep learning. This article mainly discuss the power of deep networks. It gives the answer to why the deep network needs to be deep. Back to knowledge distillation. Why does it work? An intuitive reason is that the teacher provides additional information to the student. It might be too hard for the student to learn that this symbol is 1, because there are some symbols similar to 1, such as 7 and 9. It's hard to require the student to output 1 for 1 and 0 for both 7 and 9. Given this image, it's too difficult for the student network to learn this. But if it asked the teacher for advice, the teacher will tell him that it is okay to be unsure what this symbol actually is. You don't have to output 1 for 1, because even the teacher can't tell the difference between 1 and 7. The student does not need to be better than the teacher. So learning 0.7 for 1 and 0.2 for 7 is enough. In this way, the small network can learn more efficiently than learning from the correct answer directly. Actually, knowledge distillation can do more magical things. Hinton pointed out that it is enough for the student to learn if the teacher told it the important relationships the student should know between the numbers. That is, the student network can still learn, even though it had never seen some of the symbols. Even if the dataset does not contain the symbol 7 at all, as long as the teacher had seen it before, it can still teach the student that 1, 7 and 9 look quite similar. Information like this might be enough for the student to learn what 7 actually is, without actually seeing the symbol 7. This is the main idea of knowledge distillation. Actually, the teacher network doesn't have to be a single large network. It can be an ensemble of multiple networks. What is ensemble? Although it is a commonly used technique in deep learning, especially in machine learning competitions, we didn't talk about it throughout this course. But this technique is very simple, so it only takes a short time to introduce the technique. The idea is simple. Train multiple models. Each model generates an output. The final output is voted by all the models. You can also use the average as the final output. Ensemble is a very good technique to use in competition. You can often achieve good ranks on the leaderboard by a very super large ensemble. That is, train 100 models, or even 1,000, and take the average. This is often used to get good results in machine learning competitions. But practically, it is kind of useless. If you trained 1,000 models, you have to run through every model to obtain one result. The computational requirement is too high. You can use ensemble in competitions, but it is impractical to use in actual systems. An alternative way is to use an ensemble for the teacher network and use knowledge distillation to reduce the size. The teacher network's output is the average of all the models in the teacher network. Then the student network will learn from the result of the ensemble. Let the student learn to approximate the output of the ensemble. Then you only have to keep this student network for further computations. This is an application of knowledge distillation. Also, there is a little trick you should know. While using knowledge distillation, you should slightly change the function of Softmax. You should include an additional parameter, temperature. We will encounter it again soon. Okay, we briefly go through the review of Softmax. What are we going to do? At the beginning of the semester, when we were talking about the classification, I introduced Softmax to everyone. What Softmax has to do is that you take every neural's output to an exponential function, and then you normalize it to get the final network output. By doing this, you can make the output of your network become a probability distribution, which restrains the final network's output value between 0 and 1. Okay, the so-called temperature means that before taking in the exponential function, each value was divided by a value t. This t, it is one kind of hyperparameters. This t is a parameter you need to tune. What's the effect of being divided by t? We assume t is greater than 1. And this t, which is temperature, is for making the original sharp and concentrated distribution a little bit smooth. Why do we let the centralized distribution become a little bit smooth? Here is an example. We assume that your y1, y2, and y3 before Softmax are 100, 10 and 1, respectively. After Softmax, you will find that y1 is the result of Softmax, y1 is 1, y2 and y3 both approximate 0. We assume that this is the output of your teacher network. You ask your student, which is your student network, to learn from this result. Then, there is no difference to direct learning from ground truth. One of the benefits of learning from the teacher is that the teacher will tell you that which classes are actually similar, to let student network not be so hard while learning. But, if the teacher's output is very concentrated, namely one of the class is 1, and the others are 0, then what is the difference to learning from the ground truth? There is no difference. So, you have to take a temperature. We assume our temperature is set to 100. And then you just divide y1, y2, and y3 by 100 to become 1, 0.1 and 0.01. For the teacher, adding the temperature won't change the result of classification. After Softmax, the highest score is still the highest score, and the lowest score is still the lowest score. The order of the output classes sequence will not change. The result of the classification will not change at all. But, the advantage is, the score of each class will be smooth and average. Then, you let the student learn from this result. Will make sense. It will be able to let the student learn well. Then, this is a little trick of knowledge distillation. Okay, let me see if any students have questions. I just find out that I made a mistake. What is it? It is that I forgot using the phone to turn on the system of everyone's leaving message. So, I hurry up now. Please allow me to open it. Okay, let me see. I just find out that the voice is out. Okay, come on, let me see. Are there any classmates? Having questions to ask? Hey, speaking of that education, in the chat room just now, we mentioned the one of the questionnaire from Ministry of Education. About that questionnaire, it suddenly brings to me that, if you feel that this Taiwanese machine learning course should be with more computing resources to make everyone do their homework smoothly, you should tell the Ministry of Education. You should tell the Ministry of Education. Okay. Well, a classmate asks that, when will TAs announce the score of homework 9? It should be announced next week. Just now. Actually, this question was answered. Okay, let me see. Okay, a student asks that, if we take the output before Softmax for training, what will happen? You can take the output before Softmax for training. In fact, someone take every layer of this network for training. You can say that, hey, I have a giant teacher network, and this is the first layer. There are 12 layers in total. There are 6 layers in the small student network. Then, I want to make the 6th layer of the student network like the 12th layer of the giant teacher network, and the 3rd layer of the student network like the 6th layer of the giant teacher network. Could it be like that? Yes, it could. Usually when you do many restrictions, you will actually get better results. Then, this is a commonly used trick in knowledge distillation. Okay, a student wants to ask questions about lifelong learning. It's okay. You can ask questions about lifelong learning. I see what your problem is. Last week, we mentioned using a generator to generate data to let the model learn. But, this model will only need to learn the old data once again. Has it achieved the purpose of lifelong learning? I can understand your question. You said what the lifelong learning wants is not to see the old data. If I generate some old data like data and add it to training data, will it violate the spirit of lifelong learning? It is a issue that different people have different opinions. If we define lifelong learning as you can't read the real old data, and if your network can generate old data like data, it didn't really save the old data. The old data like data was generated by itself. At least today in lifelong learning's community. If you want to write the lifelong learning paper, it is accepted as a lifelong learning method. Because you don't really use the old data. The old data like data is generated. A classmate asks that, if there is too much difference between the student and the teacher, can we add an intermediate network To let the students learn from that network? Yes, we can. It's possible. That kind of technique. A minute later in TA's video, will be brought up to everyone that there is such a way. A classmate asks that if T is too large, will the model change a lot? If the temperature is too large, will it change a lot? Yes, it will. You could think about that. If your temperature is close to infinity, then all the scores of the classes will become almost the same. So, the student network can't learn anymore. So, T is another hyperparameter. Like learning rate, it is a parameter you need to tune when you are doing knowledge distillation. Okay, a student asks that. To teacher, is the distillation of ensemble only a way to combine logistic? I guess what this classmate wants to ask is below. By doing ensemble. As my example, when I told you what ensemble is, I meant that we could average the outputs of a lot of networks. This is a kind of ensemble. Is there any other way of ensemble? Yes, actually there is. But it is a long story to tell later. This ensemble technique, in fact, was mentioned in my previous video record. Actually, it was mentioned. Later on, I will post this video record to the club to let everyone to investigate it. Actually, about ensemble, there are many different kinds of forms. For example, when you are doing ensemble, what we just mentioned is averaging the outputs of the networks. But, in fact, there are other ways to do. For example, have you seen someone directly averaging parameters of networks? The method of averaging parameters of networks. In this course, you have even used in the homework of translation. The program provided by the TAs has done the ensemble for you. It is to average different parameters. It is such a little trick. About this trick on translation, somehow, it's particularly useful. So, in TA's program, there is an implementation of this method. Okay, I hope I answered all your questions well. Okay, if there is no more question, I will continue the lecture. The rest, which is related to the network compression, doesn't remain much. We will go through it quickly. Next, we can play TA's video record. Okay, next trick we are going to tell everyone is quantization of parameter. But this trick can't be used in our homework. Why is it not useful in our homework? Because the restriction on the size of your network in our homework doesn't depend on the size of the network itself. It depends on how many parameters you use. So, if you don't reduce the number of the parameters, but simply use other methods to compress the network, you won't get better grades, which is not advantageous in this assignment. Okay, but let me introduce it to everyone. The practice of parameter quantization. The practice of parameter quantization. What does it mean? It means that if we can use less space to store a parameter. For example, when you save a parameter, you may be using 64 bits or 32 bits. Is it really necessary to have such high accuracy? Will 16 bits be enough? Will 8 bits be enough? Will even fewer bits be enough? So parameter quantization, the easiest way is as the following. For example, if you saved the network, you stored a value in 16 bits. Now, change to 6 bits or 8 bits to store a value. Hey, your storage space and the size of your network are only half of it. What about your performance? It won't drop a lot. Even sometimes, you reduce the precision of your parameters. The result will be slightly better. Okay, there is one method to further compress your parameters. It is called weight clustering. What does weight clustering mean? Let's give you an example directly. Suppose these are the parameters of your network. And then, you just do clustering. You just cluster according to the value of these parameters. If the values are close, you put them in a group. How many groups do you want to divide into? You will set it up in advance. For example, we set it up in advance that we have to divide into 4 groups. Then you will find that the relatively similar numbers are treated as a group. Then for every group, We all use only one value to represent it. That is, as long as they belong to the yellow group. We don't care what its value is. Let's say it's all minus 0.4. Anyway, others parameters might also follow the result of minus 0.4. Maybe the results are similar. This minus 0.4 may be the average of all the values in it. If the average of all the numbers in it is minus 0.4, we just use minus 0.4 to represent all the yellow parameters. Use 0.4 to represent all blue parameters. Use 2.9 to represent the parameters assigned to the green group. Use minus 4.2 to represent the parameters assigned to the red group. What are the benefits of doing this? The advantage of this is, when you saved your parameters, you just have to remember two things. One is a table. This form is the record of what the value represented by each group is. What about the other one? What you want to record is, which group does each parameter belong to? Suppose you set a smaller number of groups. For example, if you set up 4 groups. When you want to save a parameter, you only need 2 bits. To save a parameter, you can save a parameter with fewer bits. It may originally need 16 bits or 8 bits. Now you can further compress it to only 2 bits to save a parameter. Okay, you can further compress the parameters. If you are familiar with communication, then you may have learned something called Huffman encoding. The concept of Huffman encoding is that, for things that appear more often, we use fewer bits to describe them. For something rarer, we use more bits to describe it. The advantage of this is something that often appears can be described with fewer bits. Rare things are used more bits to describe. So on average, the number of bits you need to save your data is reduced. So this is Huffman encoding. So you can use these techniques to compress your parameters. This can make the space required to save every parameter become relatively small. Okay, to what extent can it be compressed? The ultimate result is that you can only take 1 bit to save every parameter. You can say the weight in your network is either +1 or -1. There are only these 2 possibilities. Nothing else. Assuming you can do that, each of your weights is only either plus or -1. Every weight you need can be saved with 1 bit. There are many studies of binary weights. I have listed some references here for your reference. We won't talk about the detail. To train this kind of binary network, the impression that most people have of the binary network is that the value of one parameter is either +1 or -1. Will the performance of this network be poor? This network should be miserable, right? It should be bad. Not necessarily. Here, we take one of the classic methods inside the binary network, which is called binary connect. Let's share its results with you. In this paper of binary connect, the author told you that he used the technique of binary connect to treat 3 image recognition problems. From the simplest MNIST, CIFAR10, which is a little bit more difficult, to the corpus designed by him. What did he find? This first row is a normal network. It is not a binary network. It is a general network. On MNIST, your error rate is 1.3%. Here is the error rate. So the smaller the value, the better. After that it is 10% on CIFAR10. He found that, using a binary connect, that is, every parameter is either +1 or -1. The result is better. So you use the binary network and get a result that was better than the result of a normal network. The possible reason is that when we used a binary network, we gave the network a relatively large limit. We put a relatively large limit on network capacity. So it's not easy to be overfitting. Therefore, using binary weights can achieve the effect of preventing overfitting. So here I want to share with you the advantage of the binary network. Okay, let's see if you have any questions. Okay. So some students asked about lifelong learning last week. We talked about the EWC method before training a new task to calculate the importance of each parameter. It will use the previous data to calculate gradient. Is it similar to the GEM, which also stores the previous data? They are different, because that gradient is not calculated after seeing the new task. That gradient is to calculate the importance of the parameter. After training for a task, you will calculate it right away. So you do not calculate the importance of each parameter with the data of old task. When you are trying to solve a new task, once the old task is finished, you immediately record the importance of the parameters. After recording the importance of the parameters, all the information of the old task can be thrown away. So it's not the same as GEM. But I had a reminder last week that if you use the EWC method, you also use extra storage space. Although it does not store data, it needs to store the importance of parameters, which will also consume some storage space. Let's talk about it in terms of the information theory. I guess you are talking about Huffman coding. Okay, you can also discuss it in terms of the information theory, or data compression, because this series of weight quantization is relatively irrelevant to the main axis of this course, so we didn't emphasize it in the homework about weight quantization. I just want to tell everyone that these techniques do exist. Some students asked how to update weight clustering. Do I need to regroup each time I update? In fact, there is a very simple way for weight clustering. You might think that weight clustering needs to be considered during training, but there is a simple way that you finish the training network first and then do weight clustering directly. But you do it directly may cause the parameters to be too different from the original parameters after clustering. One of the ways to do that is by requiring the network parameters to stay close to each other. During training, you can let the quantization be part of the loss, directly integrated into your training process, to achieve the effect of clustering the parameters during training. This is something that can be done. Someone asked, to what extent can we compress the model so as not to lose too much information? This depends on your decision. You'll have to decide how much do you want to compress it. It is inevitable that some information will be lost during compression. Thus, it is up to you to decide how much information loss is tolerable for your application. In weight clustering, how to determine the value for each cluster? Do we just take the average of values in the clusters after deciding their regions? Yes, precisely. We take the average. Someone asked, would it be better if we add differ to the binary weight? Sorry, I'm not sure what you mean by differ. Okay, someone else asked a question regarding EWC. He would like to ask whether there would be a conflict between the importance of different task data, and if so, how to merge the importance of different tasks. Here, the solution of merging the importance of different tasks, provided in the paper, is simpler than you think. An importance score would be calculated for each task. We simply need to add up the importance of all tasks. Each parameter would get a first value, b, after the training process had been done for each task. We add up the b of each task, and that's it. I hope that answers your question. Someone said that differ is about adding noise would keep more information instead. Well, I haven't seen any research about adding noise to the binary weight, so I don't have a good answer to that. That sounds like a pretty creative method. Acknowledge me if you got some result out of it. Okay, I hope I've answered all of your questions. Let's continue. Next, I want to talk about reducing the number of parameters. Through designing different network architectures, we will introduce something called depthwise separable convolution. This will be the main point of focus for the homework. You'll have to rely on this method to achieve the strong baseline. Okay. Before we talk about this method, let's do a quick review on CNN. At the beginning of the semester, we talked about CNN. We said that, in the convolution layers of CNN, the input for each layer is a feature map. In this example, the feature map has two channels. If the feature map has two channels, the height for every filter also has to be 2. Also, the filter is a cube, not a rectangle. The thickness of the filter must match the number of channels. We then scan through the feature map using the filter and get another matrix, which is represented by the square. The number of filters we have and the number of channels of the output feature map are the same. Here, we have 4 filters, which are all cubes. Correspondingly, the output feature map has 4 channels. How many parameters are there in this example? We have a total of 4 filters, and the number of parameter for each filter is 3 times 3 times 2. Pay attention to the fact that each filter is actually a cube. So, the total amount of parameters is 3 times 3 times 2 times 4. 72 parameters in total. The method I'm going to introduce is called depthwise separable convolution. What makes that a good method? We'll talk about its principle later. Before that, let's first talk about its operation. There are 2 steps in depthwise separable convolution. The first step is called depthwise convolution. What does it do? What it does is creating one filter for every channel. Each filter only manages one channel. Because each filter only manages one channel, the number of filters and the number of channels would be the same. For example, in the depthwise convolution layers, if the input feature map has 2 channels, we would only put 2 filters. That's unlike normal convolution layers, where the number of filters has nothing to do with the number of channels. In the example in the previous slide, although there were only 2 channels, we could have 4 filters. However, in depthwise convolution, the number of filters and the number of channels are the same. Each filter is only responsible for one channel. Actually, I think depthwise convolution is more aligned with the incorrect concept of CNN that people normally have in mind. People who aren't familiar with doing convolution usually mistook depthwise convolution for the algorithm of convolution. You have already taken this course, and you know that is not the case. We've spent a lot of time introducing CNN to everyone. So you must know that CNN is not done like this. But, there is a special variation of CNN that reduces the number of parameters. In fact, it's pretty similar to people's misunderstanding of CNN. That is, each filter only manages one channel. How does a filter only manage one channel? Suppose this light blue filter manages the first channel. The light blue filter scans over the first channel and calculates a feature map. The dark blue filter manages the second channel. It does convolution on the second channel, and we get another feature map. So, in depthwise convolution, the number of filters and the number of channels would naturally be the same. This is different from the normal convolution layer. In a normal convolution layer, the number of input and output channels can be different. But, in depthwise convolution, the number of input and output channels are exactly the same. However, you will encounter a problem if only depthwise convolution was implemented. The problem is the lack of interaction between channels. Suppose there exists a pattern that could only be seen across channels. Depthwise convolution is useless against cross-channel patterns like that. What do we do now? We add pointwise convolution. What is pointwise convolution? Let me explain. We now have a bunch of filters, which is the same as the normal convolution layer. But, there is now a restriction on the size of the filter. The size of its kernel is always 1 by 1. In the normal convolution layer, the filter size might be 2 by 2, 3 by 3, or 4 by 4. However, in pointwise convolution, the size is limited to 1 by 1. The purpose of the 1 by 1 filter is to consider the relationship between different channels. So, the first 1 by 1 filter would scan through the feature map we got from Depthwise convolution, and generate another feature map. Okay, there are 3 other filters here, and they would do the same thing. Each filter will generate one feature map. So, pointwise convolution can have different amount of input and output channels, which is the same as the normal convolution layer. However, pointwise convolution has a very big limitation. We force the size of the filter to be 1 by 1. It only needs to consider the relationship between channels. The relationship within the same channel is not considered. Depthwise convolution would be responsible for considering the relationship within the same channel. Thus, pointwise convolution would only focus on the relationship between channels. Okay, let's calculate the number of parameters when using this method. For depthwise convolution, the 2 filters are both 3 by 3 in size. So the size is 3 times 3 times 2. There are 18 parameters in total. For pointwise convolution, there are 4 filters that are 2 in size. Each filter only uses 2 parameters. So there are 8 parameters in total. Okay, the images on the left represent the normal convolutions. The images on the right represent the combination of depthwise and pointwise convolution. Let's compare the difference in the number of parameters between them. Let's assume that the number of input channels is I, and the number of output channels is O. And these 2 cases both have k by k for their kernel sizes. If we're doing a normal convolution, how many parameters do we need? If there are I input channels and O output channels, using k by k kernels, we can first calculate the size of each filter. The size of each filter should be k times k. Then, the kernel size multiplied by the number of input channels would be k times I. If we want to output O channels, we would need O filters in total. So the total number of parameters is the number of parameters per filter multiplied by O. If it is a depthwise plus pointwise convolution, how to reach I input channels and O output channels? Depthwise convolution's filter. Its filter does not have thickness. Its filter has no thickness. So you will find that adding up all the filters of depthwise convolution, its parameter count is only k times I, the same as one of the filter in a normal convolution. On the other hand, pointwise convolution has I times O here. If the number of your input channels is I, the height of each 1 by 1 convolution will be I. Where did O come from? Suppose you want to output O channels. You will have O 1 by 1 convolution. So pointwise convolutions total parameter count is I times O. Compare the two. You divide k times I plus I times O by k times I times O. You divide the two. After some calculations, you will find that the ratio of the two is 1 over O plus 1 over k times k. Because O is usually a large value, the number of your channels may be 256 or 512. We can ignore this 1 over O for now. K times k is usually, in this expression, a more critical value. The size of this whole expression may relate more to 1 over k times k. Suppose your kernel size is 3 by 3, or 2 by 2. If you choose 2 by 2, changing the general convolution to depthwise and pointwise convolution, the network size becomes 1 over 2 times 2. If your kernel size is 3 by 3, when you go from convolution to depthwise and pointwise, your network size becomes 1 over 9 of the original size. Okay, the next thing I want to explain to everyone is, why is this trick useful? Where did this trick come from? Actually, this depthwise plus pointwise trick has its origin in the past. There was already a method preceding depthwise separable convolution. It uses low-rank approximation to reduce the number of parameters of a network layer. If you don't know what low-rank approximation is, it doesn't matter. I'll tell you directly. How does this work? Suppose you have a certain layer. This layer has n input neurons and m output neurons. If either n or m is very large, let's say that m is very large, the number of your parameters will be very impressive. For the parameter count w, assuming there are n input neurons and m output neurons, what is the parameter count? What is the number of parameters between these two layers? It's n times m, right? As long as one of n and m is big, W has a lot of parameters. How to reduce the number of parameters? There is a very simple way. Insert another layer between n and m. No activation function is needed for this layer. Insert one more layer directly. The number of neurons on this layer is k. Originally, there was only one layer. Now we split it into two layers. The first of these two layers will be represented as V. We use U to represent the second layer. You might think, splitting a one-layer network into a two-layer network, shouldn't the number of parameters increase? You can calculate it carefully. This two-layer network actually has fewer parameters. Why? The original network's parameter count is m times n. Now we split it into two layers. The first layer is n times k, right? N times k. The second layer is k times m. K times m. If k is much smaller than m and n, you will find that the sum of parameters of u and v is much less than w. W is n times m. The parameters of u plus v is k times n plus m. N and m are not multiplied together. As long as k is small enough, the parameter count of u plus v will become less. So, often, the usual practice in the past is, if n equals 1000 or m equals 1000, it's okay. I can insert k equals 20 or k equals 50. The number of parameters will be reduced quite a lot. Although a method like this can reduce the number of parameters, of course, it has some limitations. What kind of limitations they are? You will find that when you disassemble W into U times V, when you split W into two layers of U and V, you reduce the possibility of W. Originally W can have any parameters, but splitting W into U and V will make the W matrices rank less than or equal to K. It doesn't matter if you don't know what rank is. Anyway, W will have some restrictions. Not all W can be used as your parameters. Your parameters will become limited. Okay, this method is a very common practice to reduce parameters. So, depthwise plus pointwise convolution actually uses the concept here, splitting one layer into two. Let's take a look at the original convolution first. In the original convolution, where did this parameter in the upper left corner of the red matrix come from? It comes from placing a red filter on the upper left corner of the feature inputs feature map. In this example, what is the number of parameters in a filter? The parameter count of a filter is 3 times 3 times 2, which is 18. You take the 18 parameters in the filter and the 18 values at the upper left corner of the input feature map and do the inner product to get the value at the upper left corner of the output feature map. So each of your filters has 18 parameters. If you disassemble it into depthwise plus pointwise, what will happen then? If it is split into depthwise and pointwise, the upper left corner of the output feature map, the value in the upper left corner comes from the output of depthwise convolution, so the value in the upper left corner comes from these two values in the upper left corner of depthwise convolution, and these two values come from the input feature map. These 9 values in the upper left corner of the first channel, and the 9 values in the upper left corner of the second channel. So how to go from here to here? You can think of it as if we have two filters. These two filters have 9 inputs and get the output. Then the output of these two filters are combined to get the final output. So originally these 18 values becomes a number. Now, it is divided into two stages. 18 values become 2 values, then become 1 value. If we look at the parameter in the lower left corner of the yellow feature map, where did the value in the lower left corner of the yellow feature map come from? It came from these two values in the lower left corner of depthwise convolution's output. And the two values in the lower left corner come from the lower left of this input feature maps. 18 values in the lower left corner. So you can think of it as, when we split general convolution into depthwise and pointwise, we can think of it as a one-layer network being disassembled into a two-layer network. So its principle is the same as what you saw on the previous slides. Low-rank approximation. We split one layer into two, and its demand for parameters is reduced. Okay, This is about the design of network architecture. In fact, there are so many papers related to the design of network architecture. These papers are also in TA's slides. TA won't elaborate on the architecture of these networks later. But in this assignment, if you can implement depthwise and pointwise convolution, splitting one layer of CNN into two layers of CNN, then you have a good chance to pass the strong baseline. Great. Let me see if you have any questions. Okay, if you don't have any questions, let's continue. The last one I want to share with everyone is dynamic computation. What dynamic computation wants to do is not the same as the previous methods. What we want in the first previous methods is simply to make the network smaller. In dynamic computation, what is the goal? In dynamic computation, we hope that the network can dynamically adjust the amount of calculation it needs. Why we want the network to freely adjust the amount of calculation it needs? Because sometimes you may want to run the same model on different devices. And the different devices' computing resources are not the same. So after you train a network, you expect that putting it on the new device will not require you to retrain the network. Because this magical model can adjust its computing resources dynamically. When there are few computing resources, it only needs low computing resources to perform operations. When computing resources are abundant, it can fully utilize the sufficient computing resources for computation. Another possibility is that, even on the same device, you will also need different computation. For example, when your mobile phone's power is sufficient, you may have more computing resources. Suppose your phone is out of power. Then, you may need to save computing resources for other things. Then, the computing resources the network be allocated to are relatively small. So even on the same device, we also want a network to adjust its demand for computing based on existing computing resources. For example, how much battery does the mobile phone have now? Okay, someone might ask, why we don't just prepare a lot of networks? Suppose we need all kinds of situations to cope with a variety of different computing resources. Why don't we train 10 networks? From the least computationally intensive to the most computationally intensive? Then, according to the state of our calculations, we choose a different network. But you know today, assuming you are on the same phone, you need to respond differently according to different situations. Then, you may need to train a lot of networks. But the storage space on the phone is limited. So today, we are going to reduce our calculations. But if you need to train a lot of networks, you need a lot of storage space. This may not be what we want. So we actually expect to let a network adjust its demand for computing resources. How to let the network adjust its demand for computing resources? One possible direction is to let the network adjust its depth freely. How to let the network adjust its depth freely? You can train. Generally, we train a very deep network. It has input. For example, when doing image classification, you give a picture as input. It outputs the result of image classification. Then, you can add an additional layer between these two layers. The job of this extra layer is to decide what the result of the classification should be, based on the output of each hidden layer. When you have sufficient computing resources, you can let this picture go through all the layers and get the final classification result. When computing resources are insufficient, you can let the network decide in which layer it will output by itself. For example, when computing resources are relatively insufficient, after the first layer, it directly goes into this extra layer 1. Then, we get the final result. How to train this network? Actually, the concept is simpler than you think. We all have labeled data when we train. Usually, during training, we only need to care about the output of the last layer. We hope its output is closer to the ground truth. But today, you can also make the ground truth closer to the output of each extra layer. Then, we add up all the distances between output and the ground truth. We add up all the cross-entropy between output and the ground truth to get L. Then, we minimize this L. It's over. Okay, for the most basic way like this, can it work well? This training method can be used. You can indeed use the training method I just talked about. Every layer is connected for training, and you take all the results to calculate the distance with the ground truth. Then, you minimize distances between the output and the ground truth. It is possible to use this method to reach dynamic depth, but it's not the best way. If you want to know the best way to do it, it's not the best way now. Suppose you want to know how to do it better. Maybe you can refer to this article on MSDNet. In addition, you can let the network freely determine its width. How to let the network freely determine its width? You set several different widths. Then, you throw in the same picture today. During training, you throw in the same picture. Each network with different width will have different output. We hope that every output is closer to the ground truth. It's over. We add up the distance between all outputs and the ground truth to get a loss. Then, we are going to minimize this loss. It's over. Here, I want to emphasize this to everyone. Although I draw 3 networks on these slides, these are not 3 different networks. They are the same network that can choose different widths. In other words, this weight is this weight. I use the same color to represent the same weight. In the leftmost situation, all neurons in the network will be used. But in the middle of this situation, you might decide not to use 25% neurons. But which neurons are not needed is decided in advance. You decide in advance. Some neurons are not used. As long as this 75% parameter is used. For 50% of neurons, we don't use them. Or, for 50% of neurons, we don't use them. And then, during training, we consider all the conditions together and get an output. All outputs will calculate their distances with the ground truth. We make all the distances as small as possible, and it's over. But in fact, you will find that it also has its problem. So some special ideas are needed to solve this problem. How to train the network. With Depthwise dynamic depth, you can refer to Slimmable's neuron network. Okay, what I just said is that we can train a network that can decide its depth and its width. But the decidability is still on the human side. You have to decide for yourself. When the battery power is less than a threshold, how many layers we use, or how wide is the network. But is there a way to let the network decide on its own? According to its environment? According to the situation? Can it determine its width or depth? There is a way. Why do we need the network to decide its width and depth itself? That's because sometimes, even if it's the same image classification problem, some images may be particularly difficult, while some images may be particularly simple. For those relatively simple images, maybe you only need to pass a layer, and the network can already know the answer. For some difficult questions, for example, for the same cat, this cat is made into a burrito. So this is a particularly difficult question. Maybe when this picture only passes through one layer, the network will think it is a burrito. When passing through the second layer, it's still a burrito. When going through many layers, the network can judge that it is a cat. If it's such a difficult problem, you shouldn't stop in the middle. So can we let the network decide on its own? This is a simple picture. So it passes the first layer and stops. This is a more difficult picture. So it has to run to the last layer before stopping. We can do this. Suppose you want to know how to do it. You can refer to the following references. Such a method like this is not necessarily limited to the situation. When the computing resources are relatively limited, sometimes even if you have sufficient computing resources, for some simple pictures, you can get the result you want with fewer layers. That's actually enough, so you can save some computing resources to do other things. It's like saying I can understand it in this class, because it's very clear that you will get points for what you do. Everyone will know what to do to get A+. Then, for the homework behind, after you get A+, maybe you don't want to do them. So you are just like the situation above. You stop in the middle. After getting A+, you just output, and your result is over. This is also human nature. I can also accept it. But it's not like this. Before this semester, the original grade is directly defined. It directly corresponds to that ranking. There's been a while that this original score did not directly correspond to the ranking. Grades were relative. Everyone was in pain. Some classmates got more than 100 points in their original scores. Wow, it turns out to be C. In the past, if it was directly distributed in proportion, only the top 1/4 people got A+. And so on. It might be a bit painful. But in this semester, we directly correspond the original score to the ranking. To make everyone's life easier. Okay, the above are the 5 techniques that I introduced to you. The first 4 techniques make the network smaller. These 4 techniques are not mutually exclusive. Actually, when you are doing network compression today, you actually have no reason to just do with one technique. You can use both network architecture and knowledge distillation. You can also do the knowledge distillation and do network pruning again. You can also do network pruning and do quantization of parameters. If you really want to compress the network to a small size, these methods are not mutually exclusive. They can all be used together. Okay, the above is an introduction to network compression. So here we finish the network compression. Let's see if you have any questions.